Imagine you're standing in a field at midnight. There's no moon, only the hush of wind and the subtle rustle of grass. Then, like a shadow with a heartbeat, it appears. A pale face, wings folded, soundless as a thought. That silence, the way the owl claims the night, has taught engineers how to quiet turbines, sharpen microphones, and even redesign robots. Tonight, we'll follow nature's blueprint, how the owl's secrets moved from forest edge to wind farm, lab, and machine. Problem: why humans needed a quieter, keener world. The modern world hums. Wind turbines spin, planes slice through air, fans cool servers, and microphones strain to isolate a single whisper in a crowded room. All of these systems battle the same enemy: unwanted noise and sloppy, inefficient sensing. Noise isn't just annoying. It drains power, limits performance, triggers complaints, and in some cases, restricts where technology can be used. Engineers wanted a better way: quieter blades, sharper directional hearing, flexible sensing and articulation. The question: where do you look when you need a 0-decibel teacher? To creatures that have solved these problems over millions of years. Cue the owl. /P. Nature's blueprint. What the owl actually does. Close your eyes and picture a barn owl on a frozen field. Its face isn't decorative. It's a living satellite dish. That heart-shaped facial disc collects sound and funnels it to ears that sit at slightly different heights and angles, creating a natural stereo with stunning precision. Owls can detect and locate a mouse under snow or grass purely by sound. Their facial ruff and tunable feathers let them aim their hearing like a parabolic microphone. Now open your hands and look at the wing. Owl feathers carry 3 subtle adaptations that turn chaotic air into a whisper. A comb-like set of serrations along the leading edge that split airflow. A soft, velvet-like upper surface that dampens turbulence. And a porous, fringed, trailing edge that breaks up vortices and muffles the final whoosh. Together, these features reduce the sharp aerodynamic noise typical of ordinary wings, the very noise that makes wind turbines and propellers roar. Researchers describe this trio as the owl's hush kit. And there's one more trick: the owl's neck. While owls can't spin a full 360 degrees, the myths suggest their neck and vertebrae allow extraordinary rotation and fine control over head position. A living coupling of flexibility and stability that robotics engineers study when they want cameras or sensors that can pan, tilt, and track with extreme precision without bulky motors. Human breakthrough. How engineers copied these tricks. The first breakthroughs came in the wind tunnel. Teams at universities and industry examined owl feathers and 3D printed combs and fringes onto test blades. One of the most promising outcomes, adding serrations and porous edges to blades, can cut broadband noise by significant amounts. In real terms, noise reductions that neighbors notice and regulators measure. In some tests, researchers shaved as much as 10 decibels off the sound of a blade. That's not a whisper. It's the difference between a leaf rustle and a lawnmower. A later wave moved into aviation and propellers. Engineers tested leading-edge serrations and velvet-like textures on small propellers and airfoils, aiming to reduce trailing edge noise that plagues drones and small aircraft. More recently, advanced studies blended owl serration geometry with other insect wing shapes to design propellers that are both quieter and aerodynamically efficient. A combination that could help everything from delivery drones to electric vertical takeoff and landing aircraft. On the sensing side, the barn owl's facial disc inspired directional microphones and acoustic arrays. By mimicking a dish-shaped reflector and asymmetrical ear placements, engineers built sensor housings that amplify faint sounds and improve directionality, useful for surveillance, wildlife monitoring, and better voice capture in noisy environments. And robotics labs, fascinated by the owl's neck, designed joints and kinematic systems that reproduce that graceful range of motion, compact, efficient, and capable of precise tracking without fattening robot necks or consuming huge power. Legacy and future. What this inspiration means for tomorrow. We're at the beginning of what could be a broad owl-inspired renaissance. Imagine wind farms that are neighbors' best friends, powerful but quiet enough to live beside schools and parks. Picture city drones that whisper past apartment windows. Think of search and rescue robots that rotate their heads with the subtlety of a predator listening for a trapped human. Combine quieter blades with better sensors, and you unlock new deployment options, new regulations, and less environmental friction. Modern materials, 3D printing, adaptive surfaces, and metamaterials mean these owl patterns can be tuned for specific frequencies, speeds, and environments. Scientists are already combining owl serrations with other bio-inspired geometries to push both silence and efficiency further. Nature plus one. But this is not a one-way street. Engineers learn from owl biology, and in turn, the engineering questions encourage new biological studies. When we ask why a feather looks a certain way, we learn more about ecology and evolution. When we prototype a quieter blade, we expose new variables for material science. It's an iterative conversation. The species teaches, we test, and nature inspires a new set of hypotheses. Next time on Inspired Minds, we'll follow a different animal that taught humans how to build shock-absorbing armor. And it's not what you expect. But before that, if this story made you hear the night differently, hit subscribe, click the bell, and share with someone who loves clever engineering. Links to the research and further reading are in the description. Thanks for listening to Inspired Minds, where nature's oldest inventions meet tomorrow's technology.